We've seen how dispersion and dipolar forces can arise in molecules. While all molecules have dispersion forces, polar molecules have dipolar forces as well. Our general rule of thumb is that more forces lead to a higher boiling point. There are examples of materials that have much higher boiling points than dispersion and dipolar forces can account for. We have to assume that there is an additional third force present in those molecules. Let's again start by looking at some boiling point data. Here is another figure from our textbook. There is a lot of data here, so let's take some time to go through it. It is a plot of boiling point on the y-axis and molecular mass on the x-axis. Remember our general premise from the discussion of dispersion forces. In a closely related series of molecules, heavier molecules should have higher boiling points. Start with the green line at the bottom. All of these have a group 14 atom, carbon, silicon, germanium, or tin, surrounded by 4 hydrogen atoms. As expected, the lightest molecule is the lowest boiling material, while the heaviest is the highest boiling. But now let's look at the black line at the top. These are the group 16 elements surrounded by 2 hydrogen atoms. Hydrogen sulfide, hydrogen selenide, and hydrogen telluride behave as expected, but hydrogen oxide, or water, has the highest boiling point, not the lowest as expected. Similar effects are seen with the blue data, the halogens bonded to 1 hydrogen. You would expect HF, the lightest, to have the lowest boiling point, but it has the highest. The red data, with group 15 elements surrounded by 3 hydrogen atoms, sees the same thing. Ammonia, NH3, is the lightest, but it has the highest boiling point rather than the lowest. So what's going on? There must be an additional force present in water, hydrogen fluoride, and ammonia that is not present in any of these other materials. This additional force would be responsible for the unexpectedly high boiling points. This force is seen in general for molecules that have NH, OH, and FH bonds. The additional force is called hydrogen bonding. Molecules that have a hydrogen directly bonded to NO or F are expected to have hydrogen bonding as an intermolecular force. They are expected to display unexpectedly high boiling points compared to similar molecules that don't have those bonds. So what's going on between the molecules in hydrogen bonding? We know that it has to be stronger than simple plus-minus attraction between 2 polar molecules. Not only does the positive hydrogen end of one molecule orient itself toward the negative oxygen end of the next molecule, there is an additional interaction between the hydrogen atom and a lone pair on the neighboring molecule. This is indicated in the diagram as a dashed line. Because of the electronegativity and small size of nitrogen, oxygen, and fluorine, the 3 elements that lead to hydrogen bonding, these hydrogen atoms have a considerable partial positive charge. They interact with specific lone pairs on the neighboring molecule, not just with the partial negative charge. They are not covalent bonds, but are somewhere in strength between a dipole-dipole force and a covalent bond.